Well, thank you. Welcome to this concurrent session on smart energy systems. My name is Adonis Yatchew. I've been a long-time member of the IAEE. I'm the editor-in-chief of the Energy Journal, and I'm delighted to have, at the moment, I believe we have 3 of the speakers here. I do not see the 4th speaker.
The 4th one is also here. She just joined.
Elsa is great. Okay, so in that case, this is the structure we'll use. The speakers will appear in the order on the program. Each one will get 20 minutes to make their presentation, and really appreciate if you did complete your presentation in that 20 minutes to ensure that those that follow get the fair share of their time. If there are questions from the audience, please use the chat function. I will try to monitor that. And when I say questions, I really mean at this point, what we're looking for is questions that issues that require clarification that makes it difficult for the listener to follow what's happening without an answer to that question at that time. Otherwise, what we will do is we'll have the discussion portion of this session once all 4 sessions are completed. So thank you very much for joining. And I will now hand it over to our first speaker. And just to confirm that on the program, that is Christian Calvillo. And he will be speaking on how the pace of adoption of electric vehicle smart charging impacts the energy system. So please go ahead, Christian.
Thank you very much, Mr. Chairman. First of all, I would like to apologize for my voice. I had a bad cold and my voice is kind of gone. So I hope it's clear enough. I'll do my best, but I'm not sure I will manage to finish my presentation. So I'll do my best. I'm going to share my slides now. And again, if anything is not clear because you cannot understand me, I won't feel offended. Just write it in the chat and I'll try to respond one way or another. So as I said, thank you very much for this opportunity. Thank you, Mr. Chairman, for the time. I'll just go very briefly to present this piece of work. It's very much a work in progress about the different impacts, different effects of the electric vehicle rollout in the UK. In particular, we'll be looking into smart charging adoption, how this impacts the energy system, and also on the rollout itself, how that impacts the energy system. I'll also introduce a little bit more other work we have been doing that my colleague is also presenting in a different session. So just a little bit of context on the UK policy landscape at the moment. You may be familiar, the UK has set net zero targets to reach by 2050 with different regional targets within the UK. With Scotland by 2045 is the ambition to reach net zero, and Wales a little bit later, but 95% by 2050. So that gives us about 30 years to reach net zero from the levels we are at the moment, which is quite an ambitious target. Relating to EVs, the UK government set up a new ban on the sale of new petrol and diesel cars from 2030. Interestingly, this is a ban that has been moved the date. It was originally by 2040. That was, I think, 2018, and then it was pushed forward to 2035. And then last year, with the recommendation of the Climate Change Committee, they moved it to 2030. Also, the National Grid, the British TSO, the system operator, expects that on pretty much a full EV penetration by 2050. So you will start buying cars from 2030, only electric vehicles, but by 2050, there will be all gone, it will only be electric. So, of course, this will bring a set of challenges. New demand on the energy, the power sector will require new generation capacity. Of course, it won't happen in isolation. You also have electrification of heat and other industry and other areas. So there will be a big increment in demand for power. Also, you need to deliver that power, so the network is most likely need reinforcements. However, it's not only that you increase the demand, it also you increase the peak of the demand. And that's where the smartness of the EV charging could potentially increase or mitigate the impacts of the EV rollout. So it's something to consider as well. You may be familiar, there are lots of studies around this area about the impacts of EV on the power sector, but they kind of stick to the power sector. And what we try to do here is to look into a wider picture of energy systems and also on other impacts on the wider economy. I'm not going to discuss a lot on the economy here, but my colleague in this other session will do. So I will encourage you to attend that as well. Keeping the focus on the energy system, we want to provide insight on this issue using the whole energy system model, the UK Times. So a little brief description of the model for those that are not familiar. Times is a fairly well-known model. It's an energy system bottom-up model, optimization model. What is interesting on this is that it is a long-term model that includes the whole energy system, all the processes, all the sectors. So it's not only the power sector, it's everything. Agriculture, land use, industrial, different industries, transport, etc. And because of this holistic approach, it's widely used to decarbonize the scenarios across the world. The UK government used the UK Times, Scottish government uses a Scottish Times, but there are versions in Portugal, in France, in Ireland, Denmark, everywhere. So it's a fairly well-known tool that allows you to respond different policy questions like, how will the system would look like in 2050 if we do decarbonize economy, electrify transport, as in this case, use hydrogen, improve energy efficiency, increase renewables, etc. And you get a picture on what will technologies will be needed and what investments will be likely to be made. Now I'm going to present the case studies and the scenarios description on this approach. As I said, we're focusing on the energy system impacts from two different perspectives. So I present two case studies here. One is focusing on the smart charging adoption rates. So how fast you reach your smart charging, considering the same penetration for all of it. So we have on the left-hand side, you may have seen my cursor, a penetration of EVs up to 2050 of 100%. So it starts slowly, but then picks up after 2030 when the ban starts of the new petrol and diesel cars. And then as we get closer to 2050, it slows down because most of it is already electric. But when you reach this point, what it changes is how smart you charge. So you have a fast case, you start charging smartly, more rapidly, a central case, and a slow case. And you can see the difference between the slow and the fast, that by, for instance, here in 2025, you're already expecting 20% of vehicles to be smart charging. However, in the slow one, that will happen until almost 2040. So it's a big gap between the scenarios. And that's what we're trying to look into here. The other case study is on the actual EV rollout speed, not necessarily in the smart charging, but on the actual uptake of the cars. So here we have the three scenarios, also on a slow uptake here, central uptake, and fast uptake, and a similar case. The difference between 5 to 7 years to reach a similar level. By 2030, 30% in the fast uptake is electric. In the slow one, that will happen until after 2035. So it's a 5-year delay there, and similar on other spots. Smart charging, it also changes a bit between the scenarios, but it's not such a dramatic change as in the other case. This I considered to match the National Grid Future Energy scenarios, which is kind of the reference scenarios in the UK for this type of analysis. So some of the results, as I said, this is a work in progress. So this is just a selection of results. We are producing more as we speak, but they're probably not quite ready yet to present. Probably the main or the most interesting one for us was the network investment needs. This considering the network investment and distribution and transmission levels. On the left-hand side, you have the case study one that was changing the smart charging. And we can see there is a big difference by the slow smart charging in comparison to the fast uptake of smart charging. So it's almost double the investment required. So it's a significant difference that you need to consider when you're planning your system to make sure that people charge in a smart way. And it's not only on the total level of demand, also on the timing of the investment is different. the slow uptake of smart charging requires more investment upfront, more investment in 2030, 2035, less so later on. On the fast, smart charging is more leveled. It's not such a big difference at the beginning. There is slightly more, but it's not as much as in the other cases. Sorry. In the uptake, it's a similar picture, but it's not as dramatic on the smart charging. So still, the slow uptake requires more investment than in the fast one. So it's a different about £3 billion here. So still considering, it's important to consider that you can save a lot of money in the long run if you try to push for a fast uptake of EVs and a smart charging at the same time. And again, similar story here on the investment timing. Other interesting scenarios are on the CO2 emissions, sectoral emissions across the time frame up to 2050. Interestingly here, I didn't put any other constraints on emissions, only on the electric vehicles. So what you can see here, first of all, is that there's like an exchange of emissions between the transport sector, which is the blue line, well, the blue block here in all these bars, relative to the power sector. So most of the emissions that you're reducing here, they translate into higher emissions in the power sector. So the overall emissions are actually quite similar to the base case. It's a small reduction, but it's not as large as you would expect. So that's quite important from policy point of view. So you make sure that you don't get emissions trading. Well, that's not the word, but you get like an unfortunate case where your efforts in one sector just are like compensated in a bad way in a different one. Apologies. Sorry. Other than that, because they all reach the same level of uptake of 100% by 2050, the final level of emissions is quite similar. And that happens the same in both case studies. So here, what we really need to consider is to make sure that if you're reducing emissions in the transport sector, the supplier of energy, which is the power sector in this case, it's also decarbonized to make sure that this reduction goes here and it's not just translated into a higher one in another place. So some future and ongoing work. As I said, this is thing that we're working on as we speak. So what we're trying to look as well is on the energy mix, how that changes, the generation capacity as well, how that increases, which technologies will be promoted more, especially in the case when you are actually decarbonizing the power sector. So it's working with the two policies together. Also changes in fuel use for car transport. That's quite interesting because that also affects the timing of the investment. The cost of electricity will increase, of course. Sorry, but the cost will be higher if you have to invest more on the network. So that will be interesting to see how that relates to the cost to the final user, which is here in the next item. And of course, other sectoral changes, how that reflects to the industries, because they also have higher cost of electricity, etc. Sorry. The other part of the work, as I said, is the economy-wide impacts of the EV rollout. This is currently ongoing. So I also encourage you to please attend the presentation of my colleague, Dr. Oluwafisayo Alabi, can spend to upgrade electricity network to support electric vehicles rollout, unlock value in the wider economy. And this only focuses on the wider economy impacts. So that's tomorrow. So I really encourage you to attend that as well. Sorry. Little time for you to have a look at the diagram. This is the approach we're taking to analyze the energy system and the economic impacts of the EV rollout. As you can see here, we use a two-model approach. The main model for the economic side is the economy-wide CGE model, and we have the times energy system model. So the idea is that we inform the models to develop our scenarios, and then the outputs of times are used to inform the CGE model. In this case, it's more on the investment of the network requirements and then we can analyze the impacts of those extra investments on the network and how that translates to different different indicators on all areas, like activities in each sector, prices, incomes at different household groups, fiscal variables, and different sectors of the economy, household distributions, how different household groups are impacted, on all sorts of social welfare indicators, which are very important for policy narratives and policy decision making. It could arguably you can say that it's even more important than the energy system impacts. So what happens with employment, what happens with the GDP, etc. This is just just to tease some of the results from tomorrow. This is the type of results that we will be presenting. I'm not going to go into a lot of detail, but what I want to show here is that, of course, with the investment in the network and the extra generation that is required, you have a higher price for electricity. But even though you have that, the overall economy benefits from the extra investment on the power sector. So it's a positive outcome altogether, with a increase on GDP, which is quite good for policy making. Also, real earnings for households is positive. So it's also positive for the households. So overall, it's beneficial for the economy, and you can make the case that it's a good investment to make this happen. So realizing EV rollout is a positive outcome all in all. Looking into employment, this is again just a quick peek of what you will see tomorrow. But you can see here is, of course, there are certain sectors that lose employment. These big bars here are car manufacturers, conventional car manufacturers. However, that reduction translates to gains in other areas. This is electric vehicle manufacturing, power sector, construction builds the network, the pylons and etc., create the roads to get to the place, etc. Construction, different services sectors. So all in all, it gets a positive picture on the economy. You lose some jobs, of course, but you gain more. And we're talking about 30,000 jobs. On some previous analysis we have developed, you get a positive 30,000 jobs from the rollout. Sorry. I'm almost done. So these are some conclusions. So here just wanted to briefly show that the smartness of EV charging and the uptake speed is quite important in terms of network investments. The smarter you are, the sooner you do it, and the higher the uptake, the better. That's kind of the main message there. And this is important, not because just are putting money into the economy, that's good, but that cost is passed down to the consumer. So we want to make sure that this is a progressive policies that is not affecting a lot, especially those that are in lower incomes. You need to try to reduce the cost as much as possible to get the prices under control as much as you can. Again, we're talking about the CO2 emissions. We saw a shift on sectoral emissions to the power sector, which is a worrying outcome, if you will. So you need to have in mind that holistic approach. You need to tackle decarbonization in all sectors at the same time. So yes, we need to analyze the impacts on the economy as well, because that's even more important potentially than the energy system impacts. And I do encourage you to attend my colleague tomorrow. That's me. This is my contact details. Please get in touch if you want to learn more, you want to collaborate, you can also download the paper. And yes, this is the details on my colleague tomorrow. So if you want to attend. That's me. Thank you very much.
Thank you very much, Christian. You were very efficient in your presentation. I'm glad to see that you lasted to the end. Excellent. So our next speaker is Stefano Zambotti. And he will be speaking on an agent-based simulator for smart retail power markets. And it's an acronym. There's an acronym for the model DUEBE. So I'm going to now pass it on to Stefano.
We can hear you. No, sorry.
Still no. There's a little arrow just next to the mute and unmute button. And when you press on there, you can select the microphone. So maybe it chooses a different microphone or not your headphones. A little upwards arrow just next to the mute button.
Yeah, it should have switched now. Can you hear me now?
Yes, perfect.
Oh, great. Okay, thanks. Yeah, let me show my presentation. So can you see the PowerPoint?
Yes, perfect.
Okay, great. So yeah, I'm Stefano Zambotti. I'm a researcher at the Institute for Renewable Energy of Eurac Research, Italy, and I'm also a PhD candidate at the Erasmus University of Rotterdam. So today I will introduce you to the DUEBE model, which stands for Digital Urban Energy Business Ecosystem. And yeah, it's an agent-based model that we developed in order to simulate smart retail power markets. And it is a model that I've developed together with Clarisse Dupont, Mohammed Ansarin, and Yashar Ghiassi-Farrokhfal. So what is a retail power market? A retail power market is where intermediaries, such as retailers, sell to end consumers the electricity that they have bought on wholesale markets. In retail power markets, consumers and prosumers can usually choose among a default retailer and a few competitive retailers. What they can do also is choose among two main categories of tariffs, which are fixed price tariffs, where the price remains fixed during the whole contract, and also variable price tariffs, where the price changes dynamically and to at least to a certain extent transmit wholesale market signals to customers. So retail power markets are quite young, and so they are the result of the process of the regulation of power markets, which started in around in the 90s, at least in OECD countries. And so far, they have fallen short. So, what do I mean by that? I mean that retail competition hasn't resulted in cost-reflective end user prices, as they hardly ever move with wholesale prices. So they don't transmit the signal from wholesale markets to end users. And so what we lose is a signal transmitting to end users whether there is scarcity or surplus of energy in the system. Retail rate design also fails to incentivize energy efficiency, as for example, that does not capture the economic value of distributed renewable generation. And therefore, this has incentivized the introduction of subsidies, for example, feed-in tariffs. But these subsidies also can also cause price distortions. What is a feed-in tariff? So a feed-in tariff is a policy mechanism which has been designed to accelerate the investment in renewable energy technologies, and it is an energy-based payment, so it's based on the kilowatt hour, and it's not based on when the energy is actually produced. The goal of the feed-in tariff is to offer cost-based compensation to renewable energy producers and provide price certainty, which is very important for project development in general. There are like different criticisms about feed-in tariffs, and I'm mentioning a couple here. So feed-in tariffs are usually too high as they have frequently failed to track rapidly changing technology costs, as we have seen in the past. The quickly falling prices of PV panels, for example. And also, feed-in tariffs are incompatible with competitive markets, as they prevent, for example, competition between different technologies and do not maximize social welfare. In fact, it has been argued that feed-in tariffs are causing some unequal wealth redistribution. So, as many experts have been saying in the last years, feed-in tariffs will gradually need to be phased out and give way to wholesale market prices. So the aim of this study is to compare feed-in tariffs with wholesale market prices as buyback prices in a smart grid context. So we are in a context where there is a lot of automation. So we assume that all the buildings have, for example, energy management systems that can monitor and control technologies. Therefore, we have high elasticity to prices, and we also have fully rational agents. What we want to do also is provide insights on the impact of different combinations of buyback prices and metering modes, and specifically on the overall consumption of our pool of customers, peak loads, and the average cost of electricity and the aggregate retail profit. To do so, we have developed this agent-based model, and so there are different studies concerning wholesale market prices, different levels of feed-in tariffs as buyback prices, and so different studies have compared these buyback prices. But the novelty here is that we do it through using an agent-based model, where we have developed a competitive scenario. I meant a competitive environment. And as you can see in the graphical representation, we have a set of retailers that all buy from the day-ahead market. So they have access to the same hourly prices. So they have the same costs. They have access to the same costs for electricity they buy. And so they buy electricity from the wholesale market, specifically from the day ahead, as I said. These retailers can also check on each other's strategies, and they react to each other's strategies. And so they all aim for profit maximization, and so they at each iteration, so at the end of each billing period, they try to come up with the optimal strategy to maximize profit. And at the bottom of the graphical representation, you see all these small houses that represent households, so prosumers or consumers, that aim at cost minimization. So at the end of each billing period, they are allowed to switch from one retailer to the other, trying to, as I said, minimize their costs. And then we have different arrows. So the black, blue, and green arrows represent the financial transactions, while the dotted arrows represent the information exchange among the different retailers that will react to each other's strategies. In our model, each retailer is specialized in a specific tariff structure. So for this study, we have 4 retailers. So one is the default retailer, which also acts as the last resort retailer, and is offering a static and flat price, which is represented by the blue line, which is a 20 cents per kilowatt hour tariff. Then we have a time of use tariff, which is represented by the red line, and it's a 2 tiers time of use tariff. So we have a price for the day, a price for the night, and then a single price for the whole weekend. Then we have also simulated more innovative retail structures, retail tariff structures, like an RTP, so a real-time price, which is following the wholesale market price, which is represented by the gray line. And in this case, the real-time price, it is basically the wholesale market price plus an additive markup. Then we also have an RTP prop, which is the real-time price with a proportional markup, and which is, as you can see, is exacerbating the wholesale market price trend, and it is represented by the yellow line. Here you can see all the different steps we go through at each iteration in the simulation. So in each iteration, we have each retailer predicting the loads, the generation of each of the potential customers, and they also estimate the wholesale market price. After they have done that, they create their own tariff pool. So as I said, they are all specialized in a specific tariff structure. So each of them is working with that specific tariff structure, and each of them is creating a set of tariffs which belong to the specific tariff category they can offer. After they have done that, they compute the customer costs, considering the tariffs that the competitors have offered in the previous time step. So they assume that the competitors will stick with the same tariff that they have offered in the previous time step. Once they have done that, they search for the most profitable tariff. So they go through their tariff pool and select the best response tariff to the competitor's strategy. And for choosing the most profitable tariff, they consider their own tariff pool, the possibility for customers to switch, and also the elasticity to prices of their customers. So how their customers can actually adapt their consumption profile. And after this, each of them is gonna post the best response tariff. So the tariff that they assume will maximize their profit. After they have done that, we have the customers that have access to this information. So they see all the tariffs that have been proposed by the different retailers. They also predict their own load and their own generation for the next billing period. And they compute the costs for each of these tariffs, and they choose the best one. So they can either stay with the same retailer they were subscribed to in the previous bidding period, or they can switch to another one. The data that we use for our simulations, as our model is a data-driven model, are demand profile and generation profiles from Austin, Texas. And so for now, we have run simulations with 25 households, and for the full year of 2018. And then we also use also market prices from the day-ahead market of Texas. And we retrieved those data from the Electric Reliability Council of Texas ERCOT. So here we have the setting of the simulations. So for this study, we set the simulations this way. We have a default retailer that is offering this flat and static tariff, which is 20 cents per kilowatt hour. The length of the simulation, of each simulation, is 100 weeks. So it's basically a couple of years. And in order to have some error in forecasting, we apply a normal distribution with standard deviation 0.1. and mean 0 to the measured data that I just mentioned in the previous slide. We can also set the number of retailers, and in this case we have the default retailer plus 1 retailer per tariff structure, which is the COU, the RTP, and the RTP prop. We also set the elasticity to prices, which is quite high, and it is high because it is like a future scenario with highly automated systems. So we assume there are energy management systems, as I said, that can really control all the different technologies within the house, and also charge an electric vehicle in a smart way, for example, so the load can be shifted. Then we have buyback prices. So for this specific study, we have a feed-in tariff for 20 cents, a feed-in tariff of 10 cents, a feed-in tariff of 5 cents, one of 1 cent, and then also the wholesale market price as a buyback price. We also have 2 metering modes. So we test all these buyback prices also in combination with net metering and gross metering. So net metering is when only the net demand is traded. So customers buy the net demand and sell the excess energy, while the gross metering is when everything is bought and all the generation is sold. And then also we also have a PV penetration of 76%. So 76% of our customers has a PV system. So this is the results section, and here I'm presenting consumption and peak loads. So as a general statement, here we can see that feed-in tariff has a way higher effect on gross metering scenarios than on net metering scenarios. So gross metering is represented by the yellow bars and the gray line, while net metering is represented by the blue bars with the orange line. And so yeah, I was saying that feed has a way higher effect on gross metering scenarios, and this is due to the fact that higher volumes of energy have to be compensated with the buyback price.
Stefano, I just wanted to let you know that you have 4 minutes.
Okay, yeah. I
Thank
should
you.
be able to finish by the time. Thanks. And then we have consumption. So what we see here is that the lower the feed-in tariff, the higher the consumption. And this is because when the feed-in tariff is low, retailers have lower costs, and therefore they offer us cheaper tariffs that lead to higher consumption, as our customers can provide demand response. Then peak loads. The lower the feed-in tariff, the higher the peak loads in gross feed scenarios. While in net feed scenarios, peak loads are quite stable. And this is also due to the fact that feed-in tariff has a higher effect on gross metering scenarios. And then a specific focus on the wholesale market price. Here we can see that under net metering with a buyback price, which is the wholesale market price, peak loads are the lowest. Then we have retail profit. And here on the left side, we have the net metering scenarios, and on the right side, we have gross metering scenarios. So what we can see is that the lower the fit, the higher the retail profit. And this is because tariffs are lower, since the feed-in tariff is lower, so lower cost for retailers, and consumption is higher. And then a specific focus on wholesale market price, the lowest profit is seen under net metering with wholesale market price as a buyback price. Then here we can see also how the different combinations of buyback prices and metering modes affect the average cost per kilowatt hour. And so we can see that the lowest cost per kilowatt hour is under net metering with the wholesale market price as a buyback price. And we see also that the lower the feed-in tariff, the higher the average cost per kilowatt hour. So this is because tariffs are lower when feed is lower, but consumption is higher and feed compensation is therefore lower. So this is the last slide, with results. So here we can also see the different profit shares of the different tariff structures. So we can see that in most cases, so in 90% of the cases, the real-time price with a proportional markup has the relative majority of profit share in the market, and it is followed by time of use tariff. So last slide, so the takeaway messages of this study. I'll start with the retailer's perspective. So from a retailer's perspective, a low feed seems the best scenario, as it leads to the highest profits. Then we have the customer's perspective. So from the customer's perspective, it's better to have net metering and no feed-in tariff. So it's better to have a wholesale market price as a buyback price, as this scenario seems to lead to the lowest cost per kilowatt hour. Then we also have the DSO's perspective, which is that high feed-in tariff under gross metering seems to lead to lowest peak loads, even though it is an unintended effect of the introduction of feed-in tariffs. And then from our perspective, net metering with wholesale market price as a buyback price seems to be the best option overall, as it leads to lowest cost per kilowatt hour. It leads to the second lowest peak loads, to the second highest overall consumption. It leads to the lowest retail profit. And then something that we haven't studied here, but it also might eliminate unequal redistribution effects, as there is no feed-in tariff that needs to be socialized. So thanks a lot. And if you have comments or questions, please ask them. Thanks a lot.
Okay, thank you very much. We will proceed to the next presentation, which will be made by Elsa Barazza. The title of the presentation is The Role of New Business Models in the Scale-Up of Smart Local Energy Systems and an Agent-Based Approach. So I will now step back. Elsa, please go ahead.
Yes, I'm going to share my screen. Okay, so I'm Elsa Barazza, and I'm a research associate at UCL Energy Institute, where I have completed my PhD in 2018. And today I will introduce you to some work that we are doing at UCL on an agent-based model called Brain Energy, which is an agent-based model of the UK power system, and which includes national and local investor and policy agents. So just first of all, a quick word about the complexity of the energy system transition to understand why it's important to use and why its agent-based models are useful. So basically the energy system transition, as I was saying, is complex, and it involves many dimensions, and it evolves in a non-linear way. So to reach net zero successfully by 2050, big changes are required in the energy sector's technological, as well as in the policy and social dimensions. And those dimensions, they need to change and evolve on their own, but the evolution of one dimension also influences the evolution of other dimensions. Second of all, to successfully meet net zero by 2050, substantial investment amounts in low carbon technologies are needed across the UK energy sector. And the Committee on Climate Change estimates that low carbon investments will need to reach 50 billion a year by 2030, and then remain roughly at that level until 2050 to successfully meet net zero. These substantial investment levels have to be delivered primarily by private sector companies. And this is a very heterogeneous group of investors. It comprises incumbent utilities, which have historically been like main investors in the UK power sector. But as those companies are facing disruptive forces over the last years, new type of investors are becoming important, such as new entrants and local investors, which comprise, for example, households and new type of business models. And all of these investors, they're different, they have different strategies and different motivations for investing in low carbon assets. And especially those investors have bounded rationality. They don't have a perfect foresight of the future, and their choices, their investment choices are affected by their own past experience and by their different expectations of future trends and prices and costs. So as I was saying, given the huge investment amounts, not only incumbent utilities are important, but also local investors, new business models, and smart local energy systems, which combine renewables with smart technologies for system flexibility. And all of these like SLES and new business models are seen as like being potentially very important to accelerate the net zero transition. In a previous study that we have done at UCL using BRAIN, we have found that SLES have several benefits on the energy system transition, and they help scaling up and ramping up the development of renewables, and hence leading to a deeper decarbonization to 2050 of the UK power sector. And they also help to increase system flexibility. However, we have found that renewable investments were not sufficient despite the growth of SLES and the introduction of local investors. And we found that the households alone were not sufficient to significantly scale up SLES. Hence, we are now updating Brain Energy by introducing new business models. For example, we have based our research, I will introduce later, aggregators, which are a new business model we have added in Brain Energy, which we have largely based on what community ownership models are, which basically allow individual participants to pull together and to share, to invest in renewable assets by sharing the upfront costs. And such models, they have they have benefits of social, economic, environmental benefits. For example, they improve access to renewables. They, because of economies of scales, they can lower costs, and they can also lower the energy costs for the community. And all of that can lead to a higher development of renewables. Having said that, agent-based models, they have several advantages to model complex transitions, and these include being able to represent different actors with different strategies, which are independent but also interact with each other in an environment. And also through agent-based models, it's possible to model agents which have bounded rationality, hence who have a limited foresight of the future. And all of that allows to kind of represent a more real-world behavior of investors involved in the energy system transition. So now we'll quickly introduce Brain Energy, which is the model we are working on, and it stands for Bounded Rationality Agents Investment Model. And so Brain is a power sector agent-based model based on the UK power sector. And it explores investment costs, security of supply, and CO2 emissions in UK decarbonization pathways on the long term to 2050. It is also, it has a very sophisticated and explicit representation of agents' strategies. Agents comprise investors and policy agents. And it is one of the first agent-based models to integrate smart local energy systems. And currently we are using BRAIN on two projects at UCL, one by UKIRK and one by EnergyRev. On one, we are exploring strategies of incumbents and new entrants in the electricity sector in the UK under different governance structures. And on the other project, we are studying how non-optimal decision-making can help to scale up less and which impacts do smart energy systems have on the decarbonization of the UK electricity sector. So now quickly on BRAIN, as I was mentioning, there are investor and policy agents, and those can be either national or local. And investors, they are heterogeneous because they are different type of organizations, they have different strategies, and they have different financial endowments. And agents, investor agents, they use an NPV calculation for their future investments. However, their investment strategies are also influenced by their bounded rationality, which means that which is represented in BRAIN by the limited foresight of the future and by their different expectations of future costs. And investor agents also have different discount rates and different return expectations from future investments. And another feature of BRAIN is that investors' investments are influenced by the success of their own past investments, and they also try to imitate successful strategies of other players. And all of that leads to two things. One is that investments are non-optimal, as we say, and also it leads to co-evolution of the policy dimension with the investment dimension. And this is because the outcomes of the investments of the investor agents, they lead to an emergent property of the system in terms of which technologies are installed and how CO2 emissions are evolving. And based on that, and based on how emissions are evolving, policy agents, they can adapt the strength of their policies. I will now show you which agents we have. So policy agents are of three types. There is a national government, there is a national regulator, and then there are local governments. And the national government, the main aim of this agent is to decarbonize the power sector, and it does that by enforcing a CO2 price and by subsidizing renewables through contracts for difference. And whenever the national government also sets interim decarbonization targets, which in BRAIN are largely based on carbon budgets by the Committee on Climate Change. And when these carbon budgets, if these carbon budgets are not met, this national government can increase the CO2 price to encourage more renewable investments. The aim of the regulator, on the other hand, is to make sure that the system is balanced and that the supply meets demand at all times. And to do that, it then can enforce capacity auctions. So basically, we model a capacity market in BRAIN. And finally, local governments, their aim is to encourage renewable investments in their local regions. And as regards to investor agents, so national agents are incumbent utilities and new entrants. Incumbent utilities, as you can see from the table, they can invest in all technologies, both high carbon and low carbon, while new entrants can only invest in renewables. And at the local level, we have households, which can invest in small scale PV and on small scale wind. And the new agents that we introduced in this latest work, which is very preliminary for the moment, is aggregators. So aggregators, what they can do is that they can only invest in renewables, and they can both participate in both market mechanisms, both contracts for differences and capacity market. And they first invest in their own region. If they are successful and they can grow, then they can scale up, and they can, scale up their investments beyond their own region. And a new mechanism which we are working on is a mechanism whereby aggregators will be able to borrow money from households to invest in, basically, they will aggregate households to invest in larger scale projects, and then households will be able to receive a return for it. So what we are trying to kindly model community ownership models, but this mechanism is still under construction. This is a very quick overview of how BRAIN works. We have incumbents and new entrants benefiting from those policy mechanisms, aggregator and households who can borrow from local energy development loans, and then their investments by aggregators and households give rise to smart local energy systems, and these are the technologies which BRAIN is currently representing. Just to give you a brief overview of how BRAIN works from the technical point of view, it runs from 2012 to 2050 with 8 time slices a year, which you can see in this table. And the spatial resolution of the model is in 3 regions. So it has London, Scotland, and the rest of the UK. So when I'm talking, for example, about local players, there's usually 1 per region. So there are 3 households, 3 aggregators, 3 local governments, 1 per region. And there's also demand-side response in BRAIN. And this is useful to study smart local energy systems. And demand-side response aims at improving system flexibility. And in BRAIN energy, households can participate in DSR. And the participation rate is exogenous to the model and is assumed to increase from 0 to 100% between 2012 and 2050. I will show you now some results of those preliminary scenarios that we are working on. So basically the aim of our scenarios has been to investigate how aggregators can help to scale up low carbon investments in the UK electricity market and to reach 2050 decarbonization objectives in the power sector. And also to understand which investors or which combination of investors can enable a successful transition. So there are 3 scenarios. The first one doesn't have any aggregators. It has national investors and local investors, only households. While the other 2 scenarios, they also include aggregators at the local level. All scenarios have a carbon price, which the government agent can increase up to 2 times when interim budgets are not met. And the difference between the 2 scenarios with the aggregators is that in the first scenarios, they can borrow at a higher rate, while in the second scenarios, aggregators are able to borrow at a cheaper rate to understand what the benefits of local development funds could be, or of new financing mechanisms which can help the scale up of local investors. So those results, which I said are still work in progress very much. These 2 graphs, they show the first graph shows CO2 emissions from the power sector. And as you can see, a deeper decarbonization of the power sector is achieved when aggregators are participating to the market, which is the blue line. And especially if the aggregators are able to access to cheaper financing for their loans. In that case, the power sector almost fully decarbonizes, and the share of electricity produced through renewables reaches 90% by 2050. With aggregator, when aggregators are not included, the system doesn't meet its target by 2050, and the share of electricity produced through renewables at 2050 is just above 60% at 2050. If we look at costs and installed capacity, we can see that electricity production costs, which is figure 3, they are at the highest level without aggregators, and this happens because in this scenario, most of the electricity is still produced through gas, and as gas has a higher marginal price, and the way that the power sector works in Brain is that it works on a merit order basis, and so the marginal plant is the one which sets the price, and in this scenario it's gas in most of the case. So that leads to highest production costs, while highest total and renewable investments are achieved in the scenario with aggregators, and where aggregators can borrow where they have a lower cost of capital. So it is this scenario here on the left. And and if we look at installed capacity, we see that aggregators, in the scenario with aggregators and the low cost of capital, is the one with the lowest gas installed capacity at 2050 and the highest share of renewables, especially offshore wind and biomass. Finally, a quick look at how the market shares of investors are evolving through the years. And we see that the scenarios where aggregators are participating in the market, they show two major impacts. And one is that the dominance of incumbent investors diminishes dramatically in both scenarios to 2050, especially in the one where aggregators have access to cheaper loans. And mechanisms which support aggregators, such as cheap loans, they allow aggregators to grow and to diversify the market more. So this scenario on the left-hand side is the one where the highest market diversification is achieved out of the three scenarios. Just to conclude, a few key insights. We found that from these preliminary results, which I was introducing to you, we found that encouraging the growth of new business model, for example, aggregators, is very important to scale up investments in low carbon technologies. And to do that, new financing mechanisms, which can unlock finance for new types of investors, they are very important, and they will be needed to support low carbon investments in the electricity sector. And we also found that introducing aggregator significantly reduced the market role of incumbents, but didn't eliminate that. And incumbents are still valuable contributors and important investors in the UK power sector. As I was mentioning, these results are very much work in progress, and we are now in the progress of continuously updating the model, and we are introducing these new mechanisms whereby aggregators will be able to borrow money from households, and this hopefully will give us an even better picture of how the structure of the market changes and how aggregators can flourish vis-a-vis other players. And we are also working on a mechanism under which incumbent utilities can reply to what happens to the evolving market condition by adapting their strategies. For example, by focusing more on, for example, by decentralizing and focusing more on local and decentralized renewable energy plants over time in response to the evolution of other type of players. And finally, from a technical point of view, we are introducing BECCS into brain if we want scenarios to reach net zero target by 2050. This technology is very important. And I forgot to mention that we are extending the time horizon of the model to 2070. This will be able to give us a better picture of the long-term transition. And as agent-based models are very cyclical and they don't give a cost-optimal scenario, it will be better to see the trend over a longer horizon up to 2070. So yes, this is, thank you for listening. And if you have any questions, please let me know in the chat.
Thank you, Elsa. So our last speaker is Theresia Perger, who will speak on dynamic participation in peer-to-peer electricity trading mechanisms in local communities.
Okay, you can hear me, and I will share my screen. You can slideshow. You can see the full screen now. Okay, so good evening from my side. My name is Theresia Perger. I am a PhD candidate at the Energy Economics Group at TU Vienna, and I'm presenting my work, Dynamic Participation in Peer-to-Peer Electricity Trading Mechanisms in Local Communities. This work is part of a case study in the Horizon 2020 project, Open Entrance. So let's start with the motivation. So an increasing number of photovoltaic systems leads to a more and more decentralized energy production, and traditional consumers can have the opportunity to become prosumers. When we go beyond individual self-consumption to collective self-consumption, we can take advantage of load aggregation, and we can further optimize the use of resources. Also, prosumers can become active participants in the energy system. Trading and sharing of PV can take place within a certain framework, for example, in energy communities or in a peer-to-peer trading mechanism, which is like a local electricity market where participants trade with each other. In the EU, we have the Clean Energy Package, and member states are obliged to enable the entrance of active participants into the market. And there's also a definition of peer-to-peer trading, yet many regulatory aspects are not clear yet. So what is the framework in this presentation? We assume voluntary participation of prosumers in the peer-to-peer trading mechanism, considering the individual willingness to pay of prosumers. PV sharing goes beyond the meter, and we have low entry barriers, so we're not considering closed systems, but the peer-to-peer trading is part of the distribution grid, of the public distribution grid. So when we look at the sketch on the left side, this should give a basic idea of our peer-to-peer trading concept. So we see prosumers, and they're all connected to the public distribution grid, and they share or trade electricity with each other. So what's the scope of this work? We want to optimize energy communities over several years, considering phase in and phase out of prosumers. And this is depicted here with the orange prosumer. We assume that local energy markets are more established in the future and that sufficient regulatory framework exists. The model I will present now is an operating model of existing prosumers who participate in an energy community or want to participate. So it's not an investment model or planning tool. So about the model, the basis of this model is the linear optimization model FreshCom, which we developed for previous work. And this model is maximizing the social welfare of a local energy community, while optimally allocating PV generation within the community, which is the peer-to-peer trading. And the allocation mechanism is determined by the individual willingness to pay of the members of the community. The members can be either private households or small businesses, and we include PV systems and battery storages in the technology portfolio. So what is the contribution of this work? So we extended FreshCom to optimize phase in and phase out of prosumers in such peer-to-peer trading communities, and we call that dynamic participation. So basically, we want to find an optimal configuration of new prosumers. So now let's move on to the modeling approach. Yeah, we assume that changes in a community can happen on an annual basis only. So there's, let's say, a deadline until that members can decide if they want to leave the community or stay. And also prospective new members can declare interest in joining. So at first, we capture the status quo of the original community. So we run the FreshCom model to derive some benchmarks, the overall social welfare of the community, as well as individual annual emissions and costs of the prosumers. So then, when the decisions about leaving or staying have been made, we use the bi-level optimization model, which is the extension of the Fresh model, to find the optimum configuration of the community. So the lower level of this bi-level problem is the social welfare maximization, which was applied in the previous step. And the upper level decides the optimal parameters of the new members, which means optimal PV capacity and optimal annual electricity demand. And after the new community is set, this process repeats for the next year. Before we go into detail of the bi-level problem, we need to define some functions. First is social welfare. It consists of two parts. The first part basically minimizes the total electricity bill of the whole community. And the second part is the peer-to-peer trading between the members, that's Q-share, which is determined by the willingness to pay of the prosumers. And how is the willingness to pay defined? It's basically a premium on top of the retail electricity price. So we have the factor W, which should represent a CO2 price, and D represents a distance factor. So it gives a preference of buying from the physically closest member of the community. And this is all multiplied with an emission factor. So basically, it tells us how much a member is willing to pay more for energy generated, renewable energy generated by the community members. And last, we need to define the benchmarks. So we have benchmarks for costs and emissions. So it's basically increase or decrease in percent compared to the previous status quo, and it's calculated for each prosumer individually. So now the upper level problem, it's also called LIDA because its bi-level problems are closely related to Stackelberg games, where the LIDA anticipates a reaction of the follower. And yeah, so the leader selects the parameters of the new prosumer, basically. And for this purpose, we have the objective function to be minimized. It's called cost emission function. It contains those delta costs and delta emissions of the prosumers. And in addition, each prosumer can choose an individual weighting factor alpha, which gives preference of if they care more about saving costs by participating in the community or saving emissions. So alpha can have values between 0 and 1. And so this alpha value is similar to Pareto optimization, where the optimum is found along Pareto front for multi-objective optimization with 2 objectives. Also, there are binary decision variables, and they tell us if a new prosumer will be part of the community or not. And here at the bottom of the slide, we have a summary of the formulation of the upper level problem. So objective function and upper and lower bounds of electricity demand and PV capacity, and like a limitation of new prosumers. So the next part is the lower level problem, the follow-up. So this is basically the fresh COM model, which maximizes the social welfare. And now it is parameterized by the leader's decision variables. So in other words, the leader anticipates how the electricity is shared within the community, and given the parameter the leader decides. So here we see the formulation of the problem. So we have the objective function and we have the constraints. So the constraints make sure that electricity demand and PV generation are covered at all points in time for each prosumer. And the other constraints relate to battery storage operation. So the lower level decides how much is purchased from the grid, how much is sold from the grid, and how is electricity shared within the community. Okay, then how is the bi-level problem solved? So there's a very common approach. It's transforming the lower level problem with its corresponding KKT conditions. So then we have a mathematical program with equilibrium constraints, and the equilibrium problem of the follower is parameterized by the leader's decision variables. And instead of the bi-level problem, we have a single level problem, which would be linear except for the complementarity conditions. So we also need to replace the complementarity conditions. That's done by using a big M transformation. So each complementarity condition is replaced by a set of inequalities with binary variables. And yeah, then we have a resulting single level mixed integer linear program, which can be solved with most solvers. Okay, before we move on to the results, we just quickly present data and assumptions. So the model is implemented in Python using the Pei-Hao package for optimization. And the case study consists of a small community setup with 6 household prosumers and 1 or 2 new prosumers. The electricity demand and PV generation input data are obtained from open source tools, so from load profile generator and renewables.ninja. Because KKT conditions are computationally expensive, we use a clustering algorithm to transform the annual hourly data into 3 representative days, so we can easily solve the problem. After it's solved, we need to basically upscale again to annual values so we can compare. The new prosumers, they're either household or business. For them, we use standardized load profiles, so H0 for household, G0 for business. And here at the bottom, we see the parameters, so the minimum and maximum PV capacity and annual electricity demand, and the willingness to pay, which is somewhere in the middle of the spectrum of the prosumers. You see also here in a graphical manner the input data, total demand, PV generation, and willingness to pay. So now we can move to the results. So we first present 2 distinct cases. The first one is when all prosumers of the old original community want to save emissions, so they want to minimize their individual emissions. We set all alpha values to 0, so it's minimizing emissions only. And then we run the model, and the result is not really surprising. So the resulting new prosumer, a household, also a household, has a high PV capacity and a low electricity demand. So there's no competition in consuming, or low competition in consuming PV generation. And this Sankey diagram here, it shows the changes for the original prosumers from before to after the new prosumer was added. So left is before, right is after. And yeah, we can see that what they're buying from the new prosumer is mainly substitutes what was previously bought from the grid. So because that's renewable generation, 0 emissions, they now produce less emissions than before, and that's what they wanted to achieve, they wanted to have. So the second case is the opposite, when prosumers want to minimize individual costs. So alpha is set to 1, and the result is basically the opposite. The PV is, so the resulting prosumer has no own PV system, but a very high electricity demand, and that's now a great opportunity to sell to the new prosumer and have lower annual costs. So we see that the prosumers sell a lot to the new prosumer, especially from what they previously sold to the grid. And the willingness to pay of the new prosumer is higher than the remuneration one would get usually for feeding PV generation into the grid. So they generate more income, and that's also what was basically desired. The next part is comparing 2 different prosumer types, household and business, and now we make use of the binary variables. So only one of them can be chosen, and we again compare the 2 distinct cases, minimizing emissions or minimizing costs. And for the minimizing emissions, the household profile was chosen, and with the typical values we've seen before, with the high PV capacity and low electricity demand. We can see here the peer-to-peer trading in detail. So we see that the business prosumer is not added to the community, and we see that the household prosumer sells a lot to the other community members. Yeah. The other case is the individual costs. There, a business profile is preferred. Again, no PV system and high electricity demand. And also take a closer look at the peer-to-peer trading. So the household is not chosen, but the business, and the business consumes high amounts from the other members. And that's because the business load profile matches better with PV generation profiles. So household profiles typically have, again, a peak in the evening, and the standard business profile doesn't have this peak. So it's better to sell to a business customer than to a household. Okay, the last part is sensitivity analysis. So we want to see the influence of the willingness to pay. And for that, we compared similar prosumer types, but with different willingnesses to pay. Now with willingnesses to pay on both sides of the spectrum, so €0 per ton CO2 and €100 per ton CO2. And yeah, we can see that the choice is very much dependent of the willingness to pay. So when we want to minimize emissions, a low willingness to pay is preferred, independent of household or business customer. And in the case of the cost minimization, a high willingness to pay is preferred, which is also quite an obvious result. Then we want to take a quick look at fairness indicators. Here I show the quality of service, which when it's won, the purchases and sales to the community are pretty much equal for each prosumer, and when it's close to zero, it's very unequal. So that's basically what it's saying. And the old community had this value, and it stayed pretty much similar for the emission case, and it increased for the cost minimization. So that's also yeah, an indicator for the performance of the community.
Teresa, you have 2 more minutes.
That's perfect, because I'm at the conclusions. So yeah, what did we find? The model is able to choose between potential prosumers. It's important to balance the needs of environmental and profit-oriented members, because the community is a place for different types of prosumers, members. So it would be good to aim for a diverse setup of actors, but ultimately the energy community has to be able to attract suitable new potential members, so it can guarantee, even with drop out of members, that it can perform over the years, and it doesn't like change costs very much. And yeah, larger communities are not as sensitive to changes. If one drops out, it's not as crucial for the other members. And the future outlook would be to analyze dynamic participation of different settlement patterns, and to analyze also what are the effects of peer-to-peer trading on the DSO and on the community manager. So thank you for your attention. I would like to point out 2 things. This model is available on GitHub. I mean, I'm still always doing some improvements, but you can still check out my GitHub page. And then there's also a link to Open Entrance, the project where this model is now developed in. Yeah, so thank you very much.
Thank you, Teresa. I'd like to begin by asking, there was a question that was posed in the chat by Chuck, and I'm wondering whether it wouldn't be more efficient if he simply restated it to everybody verbally. Would you be able to do that? Chuck, are you there? Well, let me try to read it, and perhaps some of you have already seen it. He says that he worked on positive energy blocks or districts, which produce more energy than they consume. Chuck, did you want to express your question in words rather than me just reading it?
Yeah, sure. Sorry, I was off the computer for a moment. Well, I found it really interesting with the presentation before, because I think the local systems is something which also now in the last presentation came up again and again. So the presumption, the interaction between players in the local context, but we found it very difficult to define the system boundary. So there was a discussion on the EU level to define what counts as a positive energy block or district or neighborhood, depending on which vocabulary was used. So I was just wondering what the definition of local energy system was in that case. But that was, I think, primarily for Elsa. But I think, Theresia, you also had a lot of parts on this in the presumption and the local transactions and peer-to-peer trading. So I think it's very closely related. It was more a curiosity than a specific question as such.
Teresa, do you have a response, and Elsa also?
You mean the system boundaries, or? Yeah, that's kind of also what I wanted to analyze with my modeling approach. When you expand the system boundaries, so you don't have a closed system, which is where you have your own infrastructure, but you have like normal prosumers, which are connected to the distribution grid, and you can slowly expand it, for example. So that was also interesting for me.
Elsa, did you want to comment on this?
Sure. For us, the way we have defined smart local systems, basically in our modeling, those are comprised of local investors, which are, for example, households or public entities, such as municipal utilities investing in their own region. And then there is a local, let's say, government body, which through different mechanisms, like a local development fund, or I don't know, grants, or other type of mechanism, tries to incentivize local investments into renewables. So yes, investors, government body, and demand side response by households to contribute to system flexibility by reducing peaks and shifting them at different times. So basically, this was our understanding of a smart local energy system. And the way we have defined them like spatially, in brain energy, that's very much stylized. So we have, as I was saying, we have 3 regions, and we have chosen them basically based on their different characteristics of renewable plants. For example, in Scotland, it's more offshore wind. In London, it's more, and the southern region is more PV. And is very, very stylized at the moment in brain energy. But based on these broader characteristics and on the participation of local agents with local government and demand side response. So
thank you. Let me just push that a little bit further. There was an article in the Financial Times just a couple of weeks ago that you may be familiar with this experiment. It's in Adelaide, where there's a local community, and the community, the households in the community have solar panels on the roof, something like a Tesla Powerwall in their basement. I think some of them have electric vehicles, but the issue is that you don't have to have a contiguous grouping. In other words, the spatial boundaries aren't essential because what they are trying to do is establish a virtual utility that allows sort of parties that are not physically necessarily all that close to each other. Would anybody, and this is an open question to anybody who would like to comment on it. So I guess the question is, to what extent do we need physical boundaries?
I think from our own research, and we've been also as well reading quite a lot around to implement this new, we call it aggregator, but to implement this new business model in Brain. And as you say, those type of players, especially when it comes to demand side management, they're very much virtual players. So they try to aggregate loads from different households and to shift the peaks. But the spatial boundaries are not so important because it's all virtual. Basically, it's platforms that take different consumers and they try to match it and move demand around to reduce peaks at certain times and shift it towards other times. If it's more based on demand side management and demand side response, spatial boundaries are less important because it's very much virtual. If it's more community ownership models, which also involve, for example, generation, then it's more physical, have assets, and then it's more location then becomes more important.
Thank you. Christian, you had your you signaled that you wanted to comment, please.
Yeah, sorry again, my voice, but just to comment briefly on that, on the boundaries, I think it's more on the governance side of things rather than the physical geographical limits. What I mean is who owns the network where you are, so you can connect to something, you need to ask someone for permissions, and your municipality might have a say on that, but may not, because the DSO is a different entity altogether and goes abroad that. So I guess governance is the big issue here on defining the questions that originally was put in place by Shark.
Okay, let me just add one more wrinkle to the story. So I have some familiarity with the system in my municipal area, which is Toronto. And what it has is a lot of various congestion points within the distribution area, even though it's not that large. And so one of the directions they're thinking about is nodal pricing, where there's actually a signal where you would benefit from, let's say, storage or some other device like demand management in a particular area. Is this something that enters into any of the models, this nodal congestion kind of pricing issue?
Nodal pricing, no. But like I included the distance factor to represent preference from buying from other prosumers who are close. So we have kind of regional aspect to this.
The other aspect that comes to mind is if you start thinking about the possibility of a grid being not a single entity, but a grid consisting of microgrids, or at least some are microgrids, then you do have a physical boundary issue, I think, because if you're going to think about resiliency of the system, where a microgrid can island itself in the case that there are shutdowns elsewhere, then you really do come up with physical boundary issues. Christian, please, you were going to comment.
Just very briefly to say that nodal pricing is less of a thing in Europe and more than North America, which I know is more of a thing. But it's interesting that somehow it needs to be put in place, if not as a price, as some sort of restrictions, if you're to manage all these smart systems together. Otherwise, it's difficult to make them cooperate between them.
Yeah. So I happen to live on a street in an old part of the city that has amongst the highest distribution level outage rates. And this is in part because of these congestion effects. Let me move on to something else. Christian, I did want to mention one thing. You might actually be aware of the work done by Christophe Bonnery, who's a recent president of the IAEE. I've seen presentations of his that specifically deal with the impacts on distribution networks in France, where he's modeling the rate at which EVs get adopted and how the distribution networks are going to have to evolve. So I just wanted to mention that. You might already be aware of that work. So next, does anybody else want to pose a question to the other speakers or make a comment? If not, let me jump in with another question. And please, whenever you're ready, speak up. You don't need to go through the chat. So this one is for Stefano Zambotti. I'm quite sympathetic to this investigation of the cost of FITs versus the other alternatives. This argument that you raised up front, or at least not necessarily that you subscribe to it, but the arguments that are raised regarding the selection of technology by sort of a higher level authority within the system, a regulator or a government, as opposed to a selection of technology decisions being made by individuals and corporations. I think that's an important part of the argument. So what I have my students do in one of my energy courses is they go to the EIA databases, they plot the adoption, the rate of adoption of renewables, and particularly wind and solar, over time, over the last 20 years, 30 years even. So they do fit countries and they do non-fit countries. And then what they do is they take a look at what's happened to residential electricity prices in that time period. So I think part of your point was that fits do drive up prices, and how do we resolve that? I think that's an important part of the debate. We here in Ontario experienced a doubling of electricity prices when we brought in fits. Now, one of the technical questions I had for you was, you were modeling, part of your modeling assumptions was a price elasticity of minus 0.3. And what I wasn't able to capture, perhaps you said it, my apologies if I missed it. Is that an intraday, or is that a short term, or is that a long-term elasticity that you're working with there? It's
hourly elasticity.
So in your model, the argument is that, let's say I have peak hours and off-peak hours, and that if my peak prices are sufficiently higher than my off-peak hours, you're going to observe a substitution to the off-peak hours at this elasticity rate.
Yeah, exactly. Yeah.
Okay, good.
So let's say that at every hour, the customers are like comparing their own tariff so the tariff they have chosen with the tariff offered by the default retailer. So based on that, they react and change their consumption.
That's very helpful. Anybody who wants to jump in with comments or questions, just please unmute yourself.
Yeah, I also have I have a question. So I'm planning to actually integrate a peer-to-peer market in the model. So like the prosumers will have the chance to switch from the retail market to the peer-to-peer market. But then, so I wanted to ask a question to Elsa and Theresia. So like, how do you see the switching from a peer-to-peer market to a retail market if the peer-to-peer market runs on a distribution grid? Like, how would you model it?
You mean switching from peer-to-peer to retail?
Yeah.
Yeah, the other way around. Okay.
Both ways. Yeah. The possibility for prosumers to switch from the retail market to the peer-to-peer market, or the other way around.
Yeah, it's difficult because you need basically two platforms, because one platform is the peer-to-peer market where you might have a community manager or something like that. And the other thing is with the retailer, which you still need if you don't have like an isolated system. So you have two contracts, and that can by nature become difficult, I would say.
Okay, so it would depend on the length of the contract. So it's like switching, would that mean like easier and quicker?
It also depends if the distribution system operator encourages peer-to-peer trading markets, and if the retailer also allows that. So that's the thing, I would say.
Okay, thanks.
Elsa, did you have anything that you wanted to add here to Stefano's question?
No, not really. It's not something we currently model in Brain peer-to-peer trading. We are thinking about introducing such a mechanism, but we are still haven't done it. And as you say, we have questions about like how to implement it based on different rules and DSOs. So at the moment, I don't have a specific answer for you. I'm sorry on that.
Okay.
So you think it would be interesting to have such a model that would have both a retail market and a peer-to-peer market competing with each other?
I would say, yeah, that would be very important. Would be very interesting to represent that mechanisms in the model. It surely, but then it will have to be very carefully like calibrated and implemented based on different market arrangements and regulations.
Yeah, thanks.
Incidentally, does anybody here know where the term prosumer comes from?
Yeah, consumer and producer, I would say.
Producers, yes, consumers, producers.
Who came up with this idea? It turns out it was a futurist by the name of Alvin Toffler in the 1980s. And I'm not sure he was thinking of electricity prosumers. And of course, the next generation in my mind is 3D printing. You know, that's a prosumer. You can do your stuff at home. Okay, just a side point. One of the general comments I had on the long-term simulations is that, and I get regularly, I get papers at the Energy Journal on long-term simulations. And I do remember cases where I was asked to testify on the construction of nuclear reactors, which is a very long-term enterprise. They have to be built over long periods of time, and they have to last a long period of time. And so, of course, there are lots of these long-term simulations around. And one of my main concerns, of course, about simulations, long-term simulations, is that you get these game-changing tipping points, as opposed to the kind of smooth projections that we have. Now, and what I'm seeing in your papers is this sensible approach of taking more than one scenario. So you're allowing for, rather than a game-changing tipping point, which is almost impossible to predict, for example, the shale revolution revolutionized natural gas and oil markets, very difficult to predict even that it will happen, never mind when it will happen. So I do like the fact that you're doing modeling under different assumptions, different scenarios. But at the heart of it, what I think is really important is to design the evolution, the regulatory setting, the legislative setting in such a way so that it responds in an agile fashion when you hit new technological innovations. And I know, I think Stefano was talking about the dramatic drop in renewable technology prices over time that weren't anticipated, actually. They weren't built into the prices that I'm paying for my electricity here. But I think it's that flexibility that's so important. And some lessons can be drawn from telecom, which has undergone a revolution over the last roughly 30 years, going from hardwired to mobile, going from monopoly to oligopoly, and maybe even oligopoly with a stronger, smaller competitive fringe. And it's really the flexibility of the regulators and governments to be willing to leave a space that's open for these kinds of innovations, so that they're not blocked out by the incumbent interests. Any other comments that you might have? Bounded rationality comes up, and that's a line of research it's a theme in Elsa's work. I have to say that one of my favorite books is Herbert Simon's Reason in Human Affairs. This tiny little book written in the 1970s and has so much in it. And if you look at it, it actually does talk about energy a bit. Now, of course, bounded rationality has come a very long way since that time. But that's sort of like that's just getting yourself in the door for my students. They would have to read that. So I enjoyed all of the papers. There's some really good work being done here. And I also enjoy the fact that, you know, there is interaction, which I hope continues amongst you. If there are any more comments or questions from you or from anyone else in the audience, please just unmute yourself.
Hello, I have a question for
Clarisse. Yes.
About the retail price. So I would like to know, could you please explain a little bit about how you get or calculate the retail price, and how the retail price in your model influence?
For the retail price, I just took an average household retail price in my model, and so that there was not much behind it. And
it's not endogenous design, or it is not?
It's an input parameter, so I did not design it. I then designed the willingness to pay for the prosumers, which is another thing. But the retail price is just an input parameter.
Okay, yeah, thank you.
Any other comments or questions? Okay, well, let me thank all the speakers and all the participants. And if we were there, we would give you a round of applause. And I look forward to seeing you live in upcoming conferences. I think the next world one is in Tokyo, and that will be a year from now. But I'm sure there'll be other conferences. And I look forward to especially seeing you who are sort of right at the forefront of the most recent research. So thank you again for participating, and also for being timely and disciplined in your presentations. So thank you, and bye for now.
Thank you.
Bye.
Bye. Bye.
Don't forget to upload your presentations, please.
And thank you, Chuck, for doing such an excellent job in keeping us on stream here properly.
It was a pleasure. Bye-bye. Have a nice day.
Bye-bye.
Bye.